Hello friends, today we're going to talk about the Jordan canonical form and generalized eigenvectors. And these concepts were very confusing to me in the beginning, but let's go through this step by step. So in a previous video, I talked about the concept of being diagonalizable. Whew, that's a difficult word to say, but important concept. So we said that a matrix A is diagonalizable if it holds this relationship, where we have a matrix that we call, for example, X, and it's invertible, and we multiply it by A and then X again, and we get a diagonal matrix here on the left. And what we found was this diagonal matrix is actually a matrix with eigenvalues on the diagonal, and that this X matrix right here holds the eigenvectors. So we said this is the eigenvectors, and these are the eigenvalues on the diagonal. And we said that this is all great, and we can use this in a lot of different scenarios, because from here, we can actually re-express A as X lambda X inverse. That's what I did here, and I just kind of multiplied by X on the left, and then X inverse on the right, and then we get A by itself. And then we saw that we can take, okay, for example, A to the n is just going to be X lambda to the n X inverse. And because lambda is a diagonal matrix, that just means that we're taking every entry on the diagonal to the nth power. So this way we can very, very quickly compute matrix powers, which has applications in, for example, Markov chains. We have differential equations and a lot of other good stuff. Now the problem is this. For this to work, our eigenvector matrix here, our X matrix, must be invertible. It must be invertible right here. And for it to be invertible, that means that it needs to have a full rank, which means it has to have n linearly independent, so n linearly independent eigenvectors. And for it to have n linearly independent eigenvectors, that means that, yeah, we need n eigenvectors for this to work. But this is not always the case. For example, if I take the matrix A, which is 1, 1, negative 1, 3, it has the eigenvalue of 2 and an eigenvector of 1, 1. And sometimes you can even say that, it has 2, 2, so we have a repeated eigenvalue right here, which would mean that we probably would want to do our eigenvalue matrix like this, our lambda. We have the repeated eigenvalue right here. And then our X, we would be like, oh great, we'll just put this first eigenvector on the first column, but then comes the problem. Like, what do we put in this second column right here? So this is kind of the issue. We can see that we're missing an eigenvector. We only have 1, but we wanted 2. And when this happens, we call that A is defective, when the number of eigenvectors is less than n in this case. And when A is defective, we don't have enough eigenvectors. That means that this is not full rank, our X matrix, which also means that it's not invertible. So if we don't have enough eigenvectors, this kind of format that we had is not going to cut it. We need to do some modification. And that's where Jordan canonical form comes in. We say that, okay, we cannot find this nice diagonal form, but we want to find something as close as a diagonal form as possible. Why? Because again, it will make taking matrix powers a lot easier. And if we can't limit it to the diagonal, maybe we can limit it to like 2 diagonals and try and do it that way. And it turns out that that's exactly possible. So we're going to say, instead of saying just A is equal to X lambda X inverse, we're going to restrict us not only to the diagonal matrices, but also the matrices with ones along the superdiagonal. So for example, if my matrix has a bunch of 2's here and a bunch of 0's, we might have 1's here along what we call the superdiagonal. And we call such a matrix J for Jordan or Jourdain, who came up with this nice theorem. So instead, we're just going to replace this thing. We're going to say, okay, A is now going to be x, J, x inverse. And we're going to kind of proceed from there. Where J, for example, in our 2 by 2 case, instead of being the 0 here, we're going to have 2, 1, 0, 2. So as you can see, it's not quite diagonal, but it's almost there. So now we kind of solved our first problem here of fixing our lambda matrix. But what about this thing right here? We know we don't find another eigenvector. So instead, we're also going to relax the conditions. We're going to say, okay, this might be a, I don't know what you want to call it, like a strict eigenvector. And the thing we're going to fill out the rest of the x, we're going to call them generalized eigenvectors. Generalized eigenvectors. And these are not the traditional eigenvectors in the sense that they are like AV is equal to lambda V, but they're quite close there as well. And here's why. So if we begin again with this equation, our new equation that we'll be working with, so we're saying A is equal to x, J, x inverse. What I can do is I can multiply by x on both sides. So that's going to become AX is equal to xj x inverse x. And that means that x inverse x is just going to go to the identity matrix. And then we're left with this form. AX is equal to xj. It's a completely equivalent way of saying what we had before, but we just get rid of the x inverse for now. And then I want to analyze what this AX and xj really means. So now we can have AX. A is our matrix, and X will be our matrix of eigenvectors and generalized eigenvectors. And the key thing here is that they're also going to be linearly independent. So in the end, when we include the generalized eigenvectors, we will have an invertible matrix. We will have a matrix of n linearly independent eigenvectors. And let me just call them like V1 and V2 in this case, for example. So we're going to have, for example, I'm going to do a 3 by 3 case. So we're going to have V1, V2, and V3. And how matrix multiplication works is that we're going to kind of multiply this thing with A, and then V2 with A, and then V3 with A. So what I can do, if I just want to look at every column by itself, it's going to look something like this. And then on the other hand, we have our xj. And now I'm going to say, okay, for the 3 by 3 case, our j is going to look something like this. We have our lambda, our repeated eigenvalue here. We got our zeros, and then we have our 1's along the superdiagonal. And now, what will I have? Well, I will have again v1, v2, v3, the columns of x. Then I'm going to have this thing. So lambda, 1 lambda, 0, 1 lambda, and so on. And what does this get us? Well, the first lambda here is going to pick out the first column. So these two are kind of related right there. And we're going to multiply v1 by lambda. So we're going to have lambda v1. And then the second column right here, we can see that this 1 is going to correspond with this v1. And then we have lambda to our v2. So this is going to turn out to be v1 plus lambda v2. And then finally, we have this one, which is going to correspond to the middle column right here, and then the lambda and the v3. So here, we're going to have v2 plus lambda v3. And now, because what we said over here, that they are equal, so these things are equal, I can also set these equality signs for all the columns. And now this starts to get pretty interesting. We see that A v1 is equal to lambda v1, and A v2 is equal to v1 plus lambda v2. Now, what does this mean? Well, this first one says that A v1 is equal to lambda v1, and this actually is our first standard eigenvector. This is just a normal eigenvector. And this is kind of in line with what we said up here, where our first column was fine, but then what? So that's where we're gonna go here. And when we say the eigenvector, what we kind of have is the eigenvector formula, right? So if I just do minus lambda v1 on both sides, we get this. We get A v1 minus lambda v1 is equal to 0, which means that I can factor out the v1, and I get A minus lambda I v1 is equal to 0. And then we kind of solve for v1 to find all the eigenvectors. Then I can kind of do the same trick here on this left-hand side. And if I do that, I'm going to get this. A v2 minus lambda v2 is equal to v1. And if I factor out the v2, I'm going to get A minus lambda I v2 is equal to v1. And if I do the same trick on this third one here, we're going to say A v3 minus, and I think I just mistyped here, so this is going to be a v3 minus lambda v3 is equal to v2. This is going to get us A minus lambda I v3 is equal to v2. And now what has happened? Well, what we can see is that, okay, for the normal eigenvector, this equation is going to turn out to be 0. But for the generalized eigenvector, we're not looking for a vector that multiplied by this thing is going to get us 0, but actually it's going to get us the previous eigenvector. And now here's the even cooler part. So this whole thing is v1. I can actually substitute it back for v1 up here. And all of a sudden, so if I take this whole thing and substitute it in for v1, what I'm going to get is the following. I'm going to get A minus lambda I, v1, which is just going to be A minus lambda I, v2. So I just substituted this in for v1, but again, this is going to be equal to 0. And now we can see that this is the same. This is just A minus lambda I squared v2 is equal to 0. And now I think this is kind of where the real magic happens. So we're saying that in eigenvector, you just have to do this equation once. We just need to take A minus lambda I one time to go to 0. But for a generalized eigenvector, we might have to do it multiple times. In this case, we need to do it twice for this vector to become 0. So we're saying that this is a generalized eigenvector of order 2. Well, this would be an eigenvector of order 1. Order 1. We're just looking at what power do we need to raise this A minus lambda I matrix to actually send this vector to 0. And we can continue with our v3. Now we can put all of this for v2 instead. Again, this is just another power. We're going to say this is A minus lambda I to the third power, v3 is equal to 0. So again, because this is to the third power, we can see that this is an eigenvector of order, or a generalized eigenvector of order 3. So what we have just discovered is a Jordan chain. As you can see, one eigenvector kind of leads to the next. So what we can say is that, okay, this might be our real eigenvectors right here, but then it might lead to generalized eigenvectors, and then another generalized eigenvectors. This one was order 1, this was order 2, this was order 3. And we kind of have a chain that links all of these ones. That we can go from maybe even the thirdest one to go to the second one to go to the actual eigenvector here at the end. So coming back to our example, we know that we found our first eigenvector by solving this equation. What vector, when multiplied by a minus lambda I, gives 0? But now we want to say, okay, a minus lambda I, v2, goes to v1 instead. So then I would just subtract by 2 on the diagonal, so we will get -1, 1, -1, 1. And then I want to solve for getting v1, which is just 1, 1. Then if I solve this, what I can do is I can add -1 of this row to this row. What we would get is -1, 1, 1. Then -1 of that, -1 of that, -1 of that, we get 0. From this top row, we say that -x plus y is equal to 1, which means that y is equal to 1 plus x. Then we can say then that v2 is going to be x, 1 plus x, which is just going to be x, 1, 1, plus 0, 1. And then I can say x to be whatever I want, so I might set it to 0. And we're left with kind of this 0, 1 eigenvector right here. So we're left with the generalized eigenvector 0, 1. And we can try it out. Because if I do 0, 1, we will pretty much pick out this first column right, or second column right here, which indeed corresponds to our eigenvector that we started with. So then we can indeed construct our x and our j and our x inverse. The first one is going to be our first eigenvector, then the generalized eigenvector, then we're going to have the j. So it's going to be 2, 0, 2, and the pesky 1 here on the top, and then the inverse of whatever we had here. So it's going to be 1, 1, 0, and -1. And then it would do all of these matrix kind of calculations. So I'm going to do them stepwise right here. And if I do this matrix multiplication, which is indeed the A that we started with right over here, 1, 1, -1, and 3. So indeed, we have succeeded by putting A into a form that's almost what we had before. It's not diagonalizable, but we have this J right over here. So that was an introduction to Jordan canonical form and the generalized eigenvectors. I hope you enjoyed. Thank you.